Section 22, Big Bang Nucleosynthesis, BBN. Protons and neutrons combine to form deuterium and helium nuclei, and a small amount of lithium in the first 5 minutes, 300 seconds, after the first 2 seconds after the Big Bang. This is called Big Bang Nucleosynthesis, BBN. We could say fine and leave the subject here and move on, but there are several reasons to learn more. To learn the composition and conditions of the universe at this time, because the conditions are different than the core of stars. Because carbon, oxygen, and other nuclei heavier than lithium were not formed at this time, but would be formed in stars later. And because cosmologists' model of the universe must be consistent with the ratio of helium to hydrogen when the universe was 5 minutes old, and this ratio can be measured from starlight today. So we will spend some time on this period. Energy density was dominated by radiation, and the scale factor was proportional to the square root of the time since the Big Bang in this period. Going from 2 seconds to 300 seconds, a factor of 150, the scale factor increased by a factor of square root of 150, or 12.25. The temperature decreased by a factor of 12.25. Radiation energy density decreased by a factor of 150 squared, or 22,500, as did radiation pressure and ordinary matter pressure. Matter density decreased by a factor of 150 raised to the 3/2 power, or 1837. So a lot was going on rapidly. For this graph, the horizontal axis is time from 0 to 300 seconds after the Big Bang. 2 seconds after the Big Bang, which is about here, the scale factor is about 3 by 10 to the minus 10th. 3 billion times smaller scale than today. From 2 seconds to 300 seconds, a factor of 150, the scale factor increased by a factor of square root of 150, which is 12.25, which I will sometimes truncate to 12. The scale factor is the blue curve with its scale on the right-hand side. The energy density of radiation, photons and neutrinos, was 1,000,000 times the energy density of matter 2 seconds after the Big Bang, and 82,000 times at 5 minutes. So radiation dominated expansion of the universe. Dark energy was utterly insignificant. The radiation energy density and radiation pressure were much higher than at the core of the Sun. I did not put the radiation energy density and radiation pressure on this graph. Neutrinos played no role in the next few minutes of the universe. Dark matter was 85% of total matter, as it is today, but dark matter played no role in the next few minutes of the universe. So, for these 5 minutes, it's all about ordinary matter and radiation. 2 seconds after the Big Bang, the energy density of ordinary baryonic matter was 2% the density of water now, or about 1/10,000th the density at the core of the Sun, and it decreased by a factor of almost 2,000 over these 5 minutes. So these are not the matter densities where fusion occurs at the core of a star. The density of matter is the gold curve on this graph, but I did not show the scale for that curve. Two seconds after the Big Bang, the temperature was 9.4 billion Kelvin, 600 times higher than the core of the Sun, but not as high as particle accelerator collisions on Earth. Temperature decreased by a factor of 12 over these 5 minutes. Temperature is the red curve on the graph with its scale on the left-hand side, from 0 to 10 billion Kelvin. 2 seconds after the Big Bang, the pressure of the kinetic energy of ordinary matter was about 13 billion atmospheres, about 20 times less than at the core of the Sun. But the radiation pressure was much higher. The pressure of ordinary matter fell rapidly. This is the green curve on the graph, with its scale on the left-hand side, from 0 to 10 billion atmospheres. So, 2 seconds after the Big Bang, ordinary matter density and pressure were lower than the core of a star, but temperature and radiation pressure were much higher than the core of a star. But all values decreased rapidly in the next few minutes. 2 seconds after the Big Bang, ordinary baryonic matter consisted of protons and neutrons, with no antiprotons or antineutrons. How did this come about? About a millisecond after the Big Bang, the temperature fell to the point where the average photon energy fell below 150 million electron volts. Quark-antiquark pairs were no longer produced. The liquid-like quark-gluon plasma evaporated to produce distinct baryon particles. Though quarks and antiquarks were believed to have been created initially in equal numbers and should have annihilated in equal numbers, leaving 0 baryons in the universe, somehow there was a small residue of protons and neutrons. Somehow 1 out of a billion antiquarks or antiprotons and antineutrons decayed to leptons, violating conservation of baryon number, but keeping the universe electrically charged neutral. This is called baryogenesis. Physicists know the 3 conditions required to cause this, some of which have been observed in experiments, but they do not know the specific mechanism and process at work in the first second of the universe. The neutron has slightly more mass than the proton, so fewer neutrons were produced than protons. Neutrino-antineutrino pairs had also stopped being created. Neutrinos decoupled from matter. Neutrino-antineutrino pairs could no longer annihilate to produce electron-positron pairs. These primordial cosmic neutrinos played no further role for most of the life of the universe. Cosmologists would like to detect these relic cosmic neutrinos. 2 seconds after the Big Bang, free protons are no longer converted to neutrons, and the ratio of neutrons to protons froze out at 1 neutron to 5 protons. There were 1.6 billion photons for every proton or neutron. 2 seconds after the Big Bang, the average photon energy was 2.2 million electron volts, so were gamma rays, which could still create electron-positron pairs, though this will end soon. Electrons and positrons played no role in the next 5 minutes, except that the net amount of electrons minus positrons exactly matched the amount of protons, so the universe as a whole was electrically neutral. This graph shows a particular Big Bang nucleosynthesis model's prediction of the mass fractions, fraction of ordinary mass, of the protons, neutrons, and other nuclei for the first 50,000 seconds, 14 hours after the first 2 seconds after the Big Bang. The horizontal time scale and vertical mass fraction scale are logarithmic. Temperature, pressure, and total ordinary matter density are falling rapidly with time. Most of the activity is complete by 300 seconds, the green vertical line. Initially, there was 1 neutron to 5 protons, or 10 protons to 2 neutrons. The mass fractions were 0.83 for protons and 0.17 for neutrons. If all the neutrons had been completely incorporated into helium-4, 2 protons and 2 neutrons, we would have ended up with 1 helium-4 nucleus for every 8 free protons. The final mass fractions would be 8 over 12 equals 0.67 for protons, and 4 over 12 equals 0.33 mass fraction for helium-4. This is close to what happens, but actually, the actual final mass fractions were 0.76 for hydrogen protons and 0.24 for helium-4. So 1 helium-4 nucleus for every 12.7 free protons. Since the helium-4 contains 2 protons and 2 neutrons, the right-hand side has more total protons and fewer total neutrons than the left-hand side. Each free neutron decays to a proton, an electron, and an electron antineutrino with a half-life of 10 minutes. So some of the free neutrons turned into protons during this period of Big Bang nucleosynthesis. 23% of the neutrons decay into protons in the first 230 seconds, before much helium or deuterium has been created. So the mass fractions of protons and neutrons became 0.87 and 0.13 at 230 seconds, and they finish with 0.76 proton mass fraction on the right. So the mass fraction for protons starts off at 0.83 and rises to 0.87 due to some of the neutrons decaying into protons. And then the mass fraction of protons falls off as the neutrons merge with the protons to form deuterium and ultimately helium. And the mass fractions end up with 0.76 for free protons, hydrogen, and 0.24 for helium-4. The top curve, this black curve, is for protons. Protons start out with mass fraction of 0.83 on the left, the red number, rise to 0.87 at 230 seconds, and finish with 0.76 on the right. Protons are stable particles, and these protons would later be hydrogen atoms and ions throughout the universe, in cosmic voids, intergalactic medium, interstellar gas, and in stars. The second dashed curve on the left is for neutrons. Neutrons start out with mass fraction 0.17 on the left, purple number, fall to 0.13 at 230 seconds due to decaying into protons, and then fall precipitously with fusion, as we will see next. That curve falls, falls, falls. A neutron is electrically neutral, and it readily binds with a proton via the strong nuclear force to form deuterium, hydrogen 2, one proton and one neutron. The binding energy of deuterium is 2.22 million electron volts. Loosely bound for a nucleus. This fusion step to form deuterium does not require the high temperatures of the cores of stars because there's no Coulomb repulsion between a proton and a neutron. Actually, it requires that the temperature be less than about 780 million Kelvin for the many high-energy photons to not dissociate the deuterium back to a proton and a neutron. This formation of deuterium was able to proceed at increasing speed from 2 seconds to 300 seconds as the temperature decreased from 9.4 billion Kelvin to 770 million Kelvin. Had there been no other fusion reactions, the final mass fraction of deuterium would have been 0.24, but there were other reactions. So, the deuterium curve is this solid black line. Deuterium gets formed, more. But at this time, instead of the deuterium plateauing to the upper right, the deuterium fraction falls off. And we cover that next. At these temperatures, a deuterium nucleus can fuse with a proton to produce a helium-3 nucleus, here, which can then fuse with a neutron to produce helium-4 nucleus. Or, a deuterium nucleus can fuse with a neutron to produce a helium-3 nucleus, which can then fuse with a proton to form a helium-4 nucleus. Or two deuterium nuclei can fuse to produce a helium-4 nucleus, either directly or indirectly. So, helium-4, this particular dashed line, takes up most of the neutrons within 300 seconds. It started off really slow. It was much less than the amount of deuterium, but growing faster, and then it achieved parity, and then finally it sucked up most of the remaining deuterium and plateaued here, the helium-4. So helium-4 takes up most of the neutrons within 300 seconds, here, and its mass fraction ends up at 0.24, as seen in the outer layers of most stars. Helium is 23.8% by mass of our Sun's outer layer. Helium that our Sun produces by fusion in its core does not get transported to its surface. Deuterium, here. Helium-3, here. And hydrogen-3, or tritium, are lesser end products of Big Bang nucleosynthesis. Deuterium and helium-3 are stable, and they exist in the universe today. But the hydrogen-3 decays to helium-3 with a half-life of about 12 years. So this hydrogen-3 is going to decay away. Helium-4 does not fuse with single protons or neutrons. However, to a small degree, it will fuse with a deuterium or hydrogen-3 nucleus to produce lithium-6 or lithium-7, which are stable. This curve is lithium-6. This curve is lithium-7. Helium-4 and helium-3 can fuse to produce beryllium-7, which is shown here, which decays to lithium-7 with a half-life of 53 days. Two helium-4 nuclei can fuse to produce beryllium-8, but it decays back to helium in less than a trillionth of a second. Because of this beryllium bottleneck, Big Bang nucleosynthesis produces no carbon or oxygen nuclei at all and is largely complete by 500 seconds. The beryllium bottleneck will later be overcome in stellar cores that fuse helium to carbon at high temperature, pressure, and density, and with the luxury of time that Big Bang nucleosynthesis does not have because of the expansion of the universe. Deuterium is 150 parts per million of hydrogen in water on Earth. Nearly all the deuterium on Earth came from the Big Bang nucleosynthesis. But none of our helium did. It came from decay of uranium and thorium. Some of the lithium on Earth came from the Big Bang nucleosynthesis, but most came from dying low-mass stars. It turns out that the solid form of molecules of lithium with deuterium is the fuel in thermonuclear bombs, and deuterium is part of the fuel for fusion reactors. Hydrogen-3 is also a fuel in thermonuclear bombs, and its half-life of about 12 years is a factor in maintaining the nuclear stockpile. It turns out that the predictions of Big Bang nucleosynthesis and the temperature and time of hydrogen plasma recombination that results in the cosmic microwave background are connected in that both processes depend on the number of photons per baryon in the universe, 1.6 billion, because the processes depend on high-energy photons. And so astronomical measurements today can quantify the photon-to-baryon ratio that has been constant since the first second after the Big Bang. Astronomers check the Big Bang nucleosynthesis predictions by using spectrometry to measure the present deuterium mass fraction in the interstellar gas in our neighborhood of the Milky Way, and the deuterium to hydrogen ratio in intergalactic gas, and the helium mass fraction of the outer layers of stars, similar to the Sun. If you're interested, you can also do some further reading on the cosmological lithium problem.